Alright, so we can get started. Just give me a second. Just testing something. Okay, so today we will actually get started with building our heart model, and in doing so, you will also learn about this new way of modeling a system called a timed automata. So if you haven't seen this before, don't worry, I'm going to explain everything on what constitutes as a timed automata. So think of this as being the analogy in the previous module, what we spent time learning, the state space model. This is the equivalent part of that, but in a completely different manner. So by the tail end of the previous lecture, I loosely laid this foundation of an idea that what we want is to do model checking, where the question that we are interested in answering is that we are given some system. In our case, the system is a combination of the pacemaker plus the heart, and we want to say whether the system satisfies certain requirements, or these requirements could be that nothing ever goes wrong. So an example is that, does my pacemaker satisfy the requirement that under no circumstances the heart rate will drop below the low rate interval? Right? That's like a requirement. Or you could say that under no circumstances you should exceed some upper rate interval. So you shouldn't enter the pacemaker mediated tachycardia. So the problem is that, and this is sort of the notion of testing versus model checking, to do this for a real system is very, very hard. Right? Because you've already implemented, and this is like in existence silicon and code right now. So there will always be a mismatch between its pattern. It would be great if my heart model behaves like the actual human heart. At the very least, I want this heart model to generate traces at the high right ventricle, high right atrium, where the lead of the pacemaker attaches, and the right ventricular apex, where also the lead attaches. So we can at least generate and predict or generate traces of different conditions of the heart, similar to the treat the symptom stuff that we did in the previous lecture. But we also want our model to respond to signals from the pacemaker, right? So it's like a two-way communication. It's not just that my mathematical model is outputting A sense and B sense. We also want to receive A pace and B pace and respond to that accordingly. So it's going to be quite an involved model, but you will see how, like with most things, something which is very complex can be broken down in a systematic way, so that we can actually, it becomes tractable and we can model individual pieces and stitch them together. And that's what we do today. So where do we even begin where do we even begin this task of modeling the electrical system of the heart? We've already narrowed down that we are not interested in modeling the biomechanics of the heart. Within the electrical system, a good starting point is this notion of action potential, which is really, if you think about it, given all what you know now, is what is driving the heart, right? It's electricity which is responsible for the muscle contraction and all of heart's behavior. And so we begin with, how can we model this action potential? And I'll be the first to say that you could actually, in principle, build a state space model to do this. Right? So there's nothing preventing you from using what you've learned in the previous module and try and apply that here. It's going to be difficult because it's not as simple as just regenerating this curve, but you could. And this is maybe left as an exercise to see if people have already tried building a LTI state space or even a nonlinear state space model of the electrical system of the heart, right? I'm not sure, maybe someone has, probably has. But what we want, our purpose of the inquiry is only to be compatible with the pacemaker, and the pacemaker, conditions apply, only looks at timing of signals. It ignores the morphology of the actual profile of the signal. So that's where we will start. So we will start with this notion that the action potential curve, which is sort of shown here, it starts with the rest period. So we can break down this action potential into a rest period into a ERP or an effective refractory period and into a relative refractory period. With the main point being that the ERP is non-interruptible, like it's like a non-preemptible task on a processor. Once it begins, you cannot interrupt it because the ions are in some certain stage. In RRP, you could actually interrupt RRP, right? So, oh my God. Yeah, let me try and fix this because it's so much better. Sorry about this. So if you look at this picture, what you are seeing is that you are in rest period right here. You go into your action potential, which is broken down into the ERP, during which you cannot be interrupted. And then once the ERP ends, we start our RRP period, which begins from sort of this point onwards. And if there was no interruption, you would go back to rest, right? So if you follow this solid black line, this is what the action potential would look like until at this point you go into your depolarization again. However, the fact that relative refractory is an interruptible period, the difference is that if you get interrupted, if your neighboring cell depolarizes during this relative refractory period, we will have a secondary action potential, but it won't be as high as the first action potential. That's the only difference. Right? Because you can think of it as, this is not how maybe you should think of it, but it would help that you have a number of cells. Once they are out of ERP, this takes some time before all of them can reach rest. And based on the percentage of cells which are available at rest, if they get interrupted again, some of the cells are not available, so unless you are at 100% rest, you won't reach your full ERP action potential. But it is interruptible is the point. And we will use this fact to start thinking about how to model a single cell, right? So we will model the refractory properties as timers, something that the pacemaker also does. So let's begin that. So this is one way of thinking about a single cell or the action potential. And this is what is called a transition system. A transition system has locations, and sometimes you will hear me say states, but don't get confused with that the state is the minimum information required to predict. Maybe that is true here, but I don't want to get into that. So let's just call them locations. We have locations, which are the three states of what an action potential is. And then we have transitions between these locations, right? So a cell goes from rest, it transitions into the location ERP, stays there for a while, transitions out into RRP, and eventually goes back to rest. Right, so very simple. This is what is called a transition system. And we are not yet concerned how long we are staying in these locations, just that this cycle exists for a cell. Right? That's our starting point. This is also what is called a finite state machine, for those who are familiar with that terminology. And then we saw this property of the heart that the tissue collectively behaves like a cell, right? It's an aggregation of cells. So we had this notion of functional syncytium, that collective behavior is as good as a single cell behavior. So we can actually model a certain part of the heart. Let's say the atrium as this transition system, and another name for this transition system is an automaton. This is what is an automaton. It's just terminology. And since you can think of this as being modeling the SA node, so the fact that I'm calling it a node automaton is only because this is trying to model the heart. In general, this is just an automaton, right? This is not a node automaton in like CS theory. People will just look at this and call this transition system an automaton. So what are some building blocks, or what does an automaton comprise of? This is just a simplified picture, but it has to be more than this to be able to actually model the properties of the atrium or the SA node, for instance. So at the very least, you would have locations or states and transitions between those states. That's what defines an automaton. But the notion of time is not yet included in this picture. And that's where time automaton comes in. The difference between a simple transition system or an automaton and a timed automaton is very simple. A timed automaton is an automaton with clocks. Okay, so what I have done now is I define a clock X, and more terminology slash representation is this dangling arrow that you will often see denotes the initial state or the beginning location of a time automata, right? You have three possible locations, you have to start from somewhere. So wherever you have this floating arrow, that denotes the start of that automaton, or start of that, the actual evaluation of the system. So what we do is we introduce a clock called X, and I set X to a value called rest default or rest definition, right? This is set to the rest period of the SA node, for instance, which would be some value or a range of values. Also, small point, when you have a colon equal to in computer science and in logic, that is read as is defined as. And a single equal to is just read as assigned as. Okay, so X assigned a certain value is different from X being defined a value. The difference is subtle, it will become clear, I assure you, in maybe a lecture. So we define X as this value, and our automaton is very simple. When you are in the rest location or the rest state, X is just counting down. Okay, it's just counting down because let's say you are the SA node, it's counting down until it expires, until the value of X becomes 0. So when you are in the rest location, there is a transition which is available for you to go to ERP. However, this transition is guarded. It's not always available. The only point when you can make this transition is when your clock has expired. So this is what is called a guard condition. So the guard condition ensures when are you allowed to actually make that transition. You can't just transition on some arbitrary value of X. If X satisfies the guard condition, you can make this transition. So the way this would work is you will be in rest. When you have exhausted your rest period, you will satisfy this guard condition, therefore you can go to your ERP state. Everybody good so far? So let me just quickly ask you, if this was all that we were doing, would this be enough to capture the behavior of a cell, the action potential? What is the big thing which is missing over here? Or let me rephrase it in another way. What happens after you reach ERP? In this picture.
Heartbeats.
Then say that louder.
The heartbeats.
No.
You can actually.
Think in terms of location. We all know that going from rest to ERP is equivalent of depolarization. But what will happen next? Once you reach the location ERP, because you made the transition, what should happen next? Just look at the slide, it's not that hard. Take your time.
You go direct to RRP because of value.
Yes, right? So what is the value of X when you reach ERP? Let's start there.
That's 30 to 0.
X is 0, right? Why is it 0? Because that's the reason why you reached ERP in the first place. You satisfied the guard condition. So when you reach ERP, what is the guard condition to get out of ERP? Same. So you will immediately go into RRP. Not only that, you will immediately come back to rest because it's the same guard condition. So clearly this is broken, right? This doesn't actually model the action potential of the cell. So something is missing. Some additional conditions slash things are required to fix and patch that. And so a transition system with clocks is a timed automata, but a timed automata also has some other properties. One very important property is if you have clocks, you must have resets for those clocks. Okay, so again, the way this is laid out actually is sort of clever, that this is how it is also coded in Simulink, right? You will use the same notation. So anything specified after a backslash is what is called a reset or an action condition. So the way to interpret this is, now when our clock expires, we were in rest, we were counting down from this rest definition. When it satisfied our guard condition, X less than equal to 0, we make this transition to ERP, but we define the value of clock to be the ERP period or ERP default interval. Right, so we are resetting the clock on this transition. So now when we are in ERP, we will start counting down from this value. and we will remain in ERP for a certain time until again we have fulfilled this guard condition. So we go to RRP, we reset to our RRP period, same thing repeats, we go back to rest and the cycle can repeat. So now our updated view of a timed automata is it's an automaton with clocks and resets, not just only clocks. So we have a guard condition, which is when is a transition legal or you can take it and you satisfy the guard condition, and we have resets. Is something still missing from our view of the action potential? Or is this enough?
That really accounts for changes in activity. It looks like they're constants.
Yeah, let's assume it's a simplified model. You are right that all of these rest periods seem to be single values or ERP sims is single value. But given that is the assumption, in terms of how an action potential is supposed to behave, do you think this is enough? Or are we missing something? Let me just tell you, we are missing something. And I'm asking, what are we missing? What is it about the action potential that we just discussed that doesn't seem to be visible on this picture of the automaton?
Interruptions?
Yes, right? So let's rephrase the question. What do we know about ERP and RRP? ERP is a non-interruptible thing, but in RRP, you are actually allowed to go back to ERP. And that doesn't seem to be happening here. There's only a unidirection transition from ERP to RRP. So it's still incomplete and we'll fix that. But before we do that, let me quickly jump onto the third and the last important object, which is also a part of what constitutes as a timed automata. Right? So far we have clocks and reset. There is one more thing which will make this complete. And for that, let me show you this different picture. So you can think of this previous automata or the one shown here as, let's say it's modeling the SA node, right? So this node over here, or region of tissue. It's not maybe actually the node. And then there could be a neighboring automaton, which is shown here, not in red, which should be able to continue this wave of depolarization, right? So the last piece of a timed automaton is that it has clocks, it has resets, and then it has something called actions or messages that it can broadcast to other automatons. So what would that message look like in our picture? Here's one example. So you should get in the picture of looking at this automaton, and in your mind you should be simulating what's happening from the initial state. So once again, we are at rest. This is our initial state. We start counting down, everything is fine. And we are talking about this top automaton right now, which is highlighted on the bottom left animation. When we are counting down, the only way we can jump out of our rest period is when our clock expires. So this is sort of trying to simulate what a SA node does, right? So this is the automaticity equivalent of what we studied previously. When we transition, not only do we reset or redefine the clock value to the ERP period, we also issue a message called depolarize to other automatons. By doing that, we are informing some other automaton, like the one shown in the underneath this red automaton in the slide, that I have depolarized, so maybe if you are listening to me, you should also depolarize to your ERP, and we'll see how that works. But this is what is called a message or an action. And so really what a timed automaton is a transition system with clocks, with resets, and with messages or actions. I use them interchangeably, both are correct. It has still, by the way, not solved this problem of how do we go back. We'll come to that. But is it clear what is the purpose of clock? what is the purpose of a reset and the purpose of a message. Maybe the purpose of the message isn't completely clear yet, because what does it mean to issue a message by a single automaton if there's nobody listening? Right? Why would you issue a message if there is no listener in general? So let's look at, if we have to model this automaton using the same transition system, how can we actually listen to messages? So the way we do that is, in the guard condition, I can actually specify that you can take this transition not only when your clock expires, but if your neighboring or some automaton has issued a depolarization message. And the syntax for that in Simulink is, you write the name of the message followed by a question mark. So this is the equivalent of listening to a message. And you incorporate this in your guard condition. Does it make sense why it's in the guard condition? So in our updated picture, now we are talking about the highlighted node. So this one may have issued the message depolarize, and I might be in rest period, but I can transition before my clock expires, because this is the OR condition. So before my clock expires, I can transition into my ERP because my neighbor has depolarized. How do I know that my neighbor has depolarized? Because I have received a depolarization message. Where was this message issued? It was issued in the action space of that automaton. So let me pause here and take questions. And let me know if you're not convinced that this would work. Yeah.
So in this case, like we have like multiple time automaton, right? So like, how do we specify that it should listen to the neighbor before it?
Very good, right? So we'll get to that. Let me repeat the question. The question is, if you had more than two of these and one of them issues depolarize, how do we ensure that you are listening to, or you have to respond to the one from above? Let's say if you have to maintain some directionality of the wave propagation, right? Is that a good?
Yeah.
So one preview of the answer, and you will see we'll run into this problem very, very soon. The preview of this answer is that everything shouldn't be called depolarize. Depolarize is not a standard syntax. It's just my speak of what this message could be, right? So you could issue one-to-one messages. It doesn't have to be a broadcast. Okay. So let's again. Let me again keep pausing if you have more questions. Is it clear why you need clocks, resets, and actions? Okay, good. I see nods, which is a good sign. Now let's actually fix the thing which was broken, because we have this ability to communicate. So let's say, it can be the case that when this depolarization message was issued by our automaton 1, you were actually in RRP at the time. This automaton was in RRP. So what we would want is that if my neighbor depolarizes and I am in RRP, I should go back when I receive that message. So that's how we fix that action potential, right? So look at this picture, and let me again do this mental sort of simulation for you. We will start. We could be either of these. This same picture applies to both of them actually. But let's say this is the SA node. So here's my first question. If you are the SA node, which one of these guard conditions is going to cause this transition to be enabled? Is it going to be your clock expiring, or is it going to be depolarization? The clock expiring, right? Because that's the property of the SA node. Because of this flow of the calcium, potassium, and sodium ions, it can automatically sort of depolarize, because it can come out of its rest period on its own. So let's say you are the SA node, you are in rest period, and your rest period expires, so you satisfy this condition. Remember, this is an OR, not an AND, so only one needs to be satisfied. When you satisfy this guard condition, we take this transition, and in doing so, we take the action by resetting our clock to the ERP definition and issuing a depolarized message. Then you are in ERP, and notice when you are in ERP, there is only one exit criteria in ERP, and that is that you have to just exhaust your ERP timer or ERP clock. Right? There is no other guard condition. This is the only way to come out of ERP. When you satisfy this guard condition to come out of ERP, we are also resetting the value of X, and we reach RRP. Now, if everything was business as usual, you would remain in RRP for this amount of time, which is a constant, and you are right, we are not taking into account activity issue. It's not real time adjusting to the human. All of that is, conditions apply. But you have to remain for whatever amount of time in RRP. If that happens, you will transition because you are now you have to go back to rest. Or when you are in RRP, you actually receive a depolarizing signal from a neighboring node, and that means you can go back. And when you go back, you reset your clock again. You also issue another depolarizing message because you are indeed depolarizing. And so I make the statement that this view of the cellular automaton is enough to capture this action potential stuff. Okay? So once again, I know this is maybe new for most of you, so the only way to get through this together is questions. Yes?
So you said that if you're in the RRP and then you get depolarized, the reaction is weaker. So don't we have to model that?
Can someone answer Sandesh's question? So the question is that we are in ERP, and when I said that, I actually even showed you, right? You are talking about this phenomena that in regular ERP will get up to this point, but interrupted ERP is less than your true action potential. So why don't we care about that? Who can answer that? Yes.
Gets reset to the same value, right? That's like the ROP gets set. It doesn't matter how far down you might move it. Once you,
Yeah, ultimately it will reset to the same ERP period, but maybe another way to rephrase is, why don't we care about this voltage difference? So who can respond to it? Or should we care about the voltage difference?
It's it doesn't matter, right? It causes the same.
What does it mean to it doesn't matter? What are we ignoring because it doesn't matter?
That threshold.
We don't care about the morphology of the signal. Okay? We don't actually care how high it is, we only care about events. So you are right that if you get interrupted, if you actually take this transition, the resulting action potential may not be as high or as equivalent to if you are coming out of rest. But nonetheless, this is an event, and we are only modeling events. We are not modeling voltages or morphology of the current. So that was a good question. Anything else?
Does the morphology that we're ignoring include the time? Is that event?
Why do you think time is getting ignored?
Because we're resetting back to the ERP.
Because you are entering ERP, right? So
Yeah.
once you, I don't want to go too far back, but if you look at this interruption, we reset to ERP again. And you are right, in the heart, you can make the case that secondary ERP period is not the same as your primary ERP, where I'm defining these terms myself. They are not cardiovascular, cardio speak, where the primary is when you come out of rest, secondary is the interrupted, and you can keep going with tertiary and whatnot. And yeah, it may be the case, but in this simplified view of the action potential, we are including that. Yeah. So it's a model assumption. Those are all really good questions. Anything else? So the main thing that you have to get used to and get a good grasp on is this interplay of guard conditions, clocks, resets, and messages. Okay? So this, I now say, is what I call a complete node automaton that can model any heart tissue for that matter, not just the SA. Okay? So this is what is called a timed automaton. You just saw this example, and you have built your first model of what a timed automaton is. It has all the key ingredients of transitions, gaps, clocks, resets, and actions. Okay, so let's look at a slightly broader view of the heart, not just this tissue level. Let's say I want to mimic the physiological signals from the heart that can be, that can be sent to the pacemaker. So in that case, I propose that I can actually use this node automaton both to model the atrium, where one of the leads is attached, and the ventricle, right? They are the same, right? They behave the same. Only difference is probably what these values of the rest periods and these messages are. But functionally, everything has the same action potential curve. So one question which is shown here is, what might be the differences between some of these default periods or even messages between the atrium node and the ventricle node? Let's just make it even more simpler. Which one of them should have a high rest period and a low rest period if we are talking about normal sinus rhythm? And you should all know what normal sinus rhythm is, right? So what's the relationship between the rest periods of them, both of them? Nothing?
Doesn't the ventricle have a longer rest period? Right? Or
Okay, the ventricle should have a longer rest period. Who can agree or disagree with them? Yeah,
I think they have the same rest period, they're just offset.
they are just offset, so there is no sort of a delay that you are thinking about. Okay, yeah.
Would you want a longer rest period in the atrium so you don't have the tachycardia?
So we are talking about normal sinus rhythm, which is the subtext of what I want you to think. So let's begin with what is normal sinus rhythm. Okay, so in a normal sinus rhythm, which of the nodes will depolarize first? Everybody should answer this, right? Otherwise we have some problem. Right? The atrium will depolarize first because of the automaticity of the SA. So if we want the atrium to self-depolarize, how will that happen in terms of this guard condition? It will have to satisfy this guard condition. Because if it's the first one to depolarize, there's nobody else who's issuing a depolarizing message. So what should its rest period be with regards to the ventricle? Lower or higher? Yeah, you can be louder, right? So all these questions are very low risk, and it's fine to be incorrect. That's how you learn. It has to be lower. It has to be lower because if it is larger than this automaton, then this will depolarize first. As simple as that, which we don't want in normal sinus rhythm. Right? So one of the things is if we had two of these automatons, so each of the atrium and the ventricle is being modeled using this node automata, we have to ensure that the rest period of the atrium is less than the ventricle. Now let me address one of the points which was brought up. Yes, both are cardiac muscle tissues, and there is no reason to believe why one would have larger rest period of the other. But don't lose sight of the fact that we are trying to model a behavior of the heart. So even though this represents a real action potential curve, we get to decide the values of these parameters to fulfill the behavior that we want to, simulate in our model. So I can say that if I want to model the heart rate of 60 beats per minute, which is normal sinus rhythm, or 72, then that means that the atrium fires once every second. So I can choose the rest period to be 1 second. So So after 1 second elapses, you will depolarize if you are the atrium, you will take this transition. And to ensure that in normal sinus rhythm, we never stand the risk that the ventricles can depolarize before the atrium, I can choose a very long period. I know it maybe doesn't make physical sense to have a 10-second rest period, but for simulation we can use that. And it would replicate normal sinus rhythm with atria V-sense, A-sense, V-sense. Okay? So that's just one aspect when you think of how we can use this building block, which is a node automata, and place it anywhere in the heart. The only consideration we have to do is how does placing it at different points in the heart influence the parameters, right? So the title of the slide is that different tissues have different properties, but they have the same building block that you can pick and patch anywhere you want to model. So let's continue this chain of thought. Another thing which was brought up, and I sort of hand-waved over that and didn't bring too much attention on purpose, is we know that in the heart there is a delay between when the atrium squeezes and the effect is observed in the ventricle. Right now, in our heart model, so let me actually make that more clear, maybe this will help. We have the same timed automata, but the top one is for the SA node, or it's not actually modeling the SA node, it's just the right atrium. I am calling it SA node to emphasize that it's being driven by the SA node, or to even indirectly emphasize something about the rest period of this automaton. But the same automaton can be copied or cloned, and it can be used to model the right ventricle, where we have established some relationship between the rest periods of the both. But let's again do this mental exercise of simulating how this would go, right? So this automaton has its own clock X, this one has its own clock Y. Here is the initial state of the entire system. We will simulate both of them together in parallel, right? Time moves at the same pace for both of them. So if this is the SA node, what should happen first is, because its rest period is less than the rest period of the ventricle, this is the first thing which comes into play, right? This is the first guard condition that will be activated. Because Y will take more time to satisfy this guard condition. So let's say we are the atrium or the SA node, our rest clock expires, this transition is enabled and taken because we satisfy one of the guard conditions. In doing so, we reset our clock to ERT of the SA node, we issue a depolarized message and we enter the ERT. At the same time, because we have issued this depolarization message, who was listening to this message? The ventricle is also listening to this message. So even though the ventricle's rest period is that ridiculous 10 seconds, because this story has already elapsed at 1 second based on our previous example, because it receives a depolarizing message from the atria, it will transition to ERT. Okay? But where is the delay? It is instantaneously transitioning to the ERT. So something is missing still if we want to replicate normal sinus rhythm. We have done everything right. We have built this Lego block of what a node automaton is, and we are placing it at different regions in the heart. We are adjusting their timers to match the property of that tissue. For one last piece is there is a delay between when the atria depolarizes and the ventricles respond. So no surprises. Guess what I'm going to say next? How do we fix this? How can we incorporate a delay between the two automatons? Can we modify, introduce more states? What can we do? I want to hear some answers.
Could you like create a like intermediary like timed automaton that like has an input that would like listen to the SA node, and then it would add a delay within the timed automaton, and then add a secondary, and have an output would listen to.
Okay, so one suggestion is to create another automaton, maybe using the same Lego block, or so you want to have another automaton with the same structure, and it would go from REST to ERP to IRP, but I guess my question would still be that the transition from the SA node to the intermediary automaton would be instantaneous, and you want to capture the delay as the loop of that intermediary automaton. Okay, I can see how that could work. Any other suggestions?
Could you just add time to the reset value?
Can you be more precise about which one and where? Or give it a shot.
Yeah, add, so to the, when you reinitialize Y.
Okay, here,
ERP def.
here or someplace else? Oh, you can't see my, here or someplace else?
That's where I was saying.
Yeah.
Yeah.
So what do you want to do here or suggestions?
Well, saying it out loud now, it doesn't sound as right, because you're still doing the transition, you're just changing the value, but I would say add a constant to that. Somewhere you add a constant, which artificially creates a delay. I'm not sure that's the right place.
You want to just modify this value, or you want to add, you are proposing that I want to add another state where this is delay, sorry about my PowerPoint dexterity, and then it goes to ERP.
Yeah, like a state where there's a fixed time.
Okay, that's a good suggestion too. Maybe room for one more suggestion before we proceed. Aaron? Any thoughts?
I really like this idea of adding an extra state in there, because then you could add another sort of definition for some time that would add a delay. So you would go to that state and you get the depolarized message, and then have another delay time or in there that would delay however long before moving to your.
Okay, so all of those are good suggestions. And really they are trying to, chip away at this problem of how do we introduce a delay. And if I have to summarize the suggestions, one idea is adding an entire automaton altogether, and the other is modifying, let's say, the ventricle in this case to account for the delay. Right? Those seem to be the two schools of thought. And they may be able to solve the problem, but I want to take this opportunity to introduce another modeling principle. Right? So the thing that we have to solve is how do we model this propagation of the electrical wave from the atrium to the ventricles. And I guess what was kind of suggested is you could think of these intermediate cells as also being automatons, and then collectively, based on their loops, you can reach eventually the ventricle, right? So you have a large number of intermediate automatons. And the other is that let's just adapt the structure of this automaton by adding some other states that make sense and solve the problem. So one very important principle in general in modeling, not just for the heart, is whenever you make a modeling choice, especially a mathematical choice, right? You have committed to building a state space model or a gray box model, you are committed to a neural network, or you're committed to something else, it's in general a very good idea to just stick with the same formalism as much as possible. Right? If things speak with each other in the same mathematical language, it will generally lead to good outcomes. And what good outcomes it will lead to will become clear later in this module. But that's the lesson learned. Right? We want to actually stick with the same formalism. So this was one of the suggestions, or maybe I tried to force you to suggest this just because I had the slide. You can decide. But okay, one suggestion was that we modify the ventricle. So let's introduce a state called, or location called delay, such that when I received the depolarized message and I was in rest from, the message was issued here, from the SA node, I transition into delay, and I reset to the delay timer, 100 milliseconds to account for the atrioventricular pause, let's say. I remain in this timer and then after the delay has been exhausted, I then go to my ERT. So this does actually solve our problem, but what it breaks is the symmetry of both these nodes. Or let me put it in another way. The delay between the atria and the ventricles is not the property of the ventricle. It's the property of the path or the conduction tissue between the two. Here, we are combining two functions into a single automata. It will solve the problem, but this is no longer a right ventricle. Right ventricle doesn't behave in this way. So while it does solve our normal sinus rhythm problem, we will not use this. We want to stick with our Lego blocks as much as possible and place them in different places rather than modify one of them based on some local problem that we are trying to solve. And like I said, more importantly, the delay is a property of the path, right? So this path between the right ventricle and the right atrium, how it behaves has nothing to do with how the right ventricle behaves. And therefore, we will actually adopt the former suggestion where let's introduce another automaton to model just this delay or model the behavior of the path. So I'm going to begin this and let's see how far we can go, and then I don't want to cover all of this because this is new material and I want to give you some time to revisit and convince yourself how everything works. So I'm going to introduce this path automaton and how everything works together, and probably end sooner today than usual. Okay, so how do we fix this? It's a busy slide, but get used to these slides now. So here is my SA node. It has its own clock X. Here is my right ventricle. It has its own clock Y. A very minor point, but let me make this point again. I could have called both of them X. It wouldn't matter. Every automaton has its own clock. When you implement it in code, it has its own workspace. They don't crosstalk. The only crosstalk is through messages. So everything can be called X, but to make it not confusing enough, I have called them a separate clock. It doesn't matter. So in this picture, we are in rest. Once again, given that this is the atrium, this is the first thing that will occur in normal sinus rhythm. We issue a depolarized message when this occurs. And what was happening before is that we were listening to this depolarized message and we were instantaneously taking this transition. But what I propose is that let's build a new automaton which represents the properties of the path between the atria and the ventricles. That's why it's called a path automaton. And just by common sense, I propose that the path is either idle or it is conducting. It can be in one of these two states. If the path is conducting, it's accounting for the delay. If not, it's just sitting there doing nothing. So what we would want is that when this depolarizing message was issued by the SA node, we go from ideal to conduct. So we have to definitely listen to the depolarized message. And after we are done conducting, we have to go back to ideal. So this is a very basic structure. It's not complete because it doesn't have clocks and resets of its own. But in principle, this is what we want the path automaton to do. So not only that, when we actually go into the conducting state, we also want to propagate the message forward, right? That I have done conducting, so now based on this propagation, you can also start your own stuff. Right now, this is not solving the problem because everything is still being called depolarized, and that doesn't help. And I think this is one of the points which was also brought forward earlier. Because when I issue the depolarized, my ventricle is still listening for that message. So let me at first just correct some terminology. So I change the message that I listen to, and I call it activate node 2, rather than depolarize. So if you look at the ventricles now, and look at each of the guard conditions, so this one, and the others don't have messages, my ventricle doesn't even listen to depolarize anymore. Okay? It only listens to a message called activate node 2, and who is issuing this message? It's the path automata. So at least what I have done is, I have decoupled the atria from the ventricle in terms of messages. So once again, let's do this mental simulation. When this is issued, because SA node depolarizes first, it will only affect the path. And so if it only affects the path, once the path automata depolarizes, it issues its own message to tell the ventricle that I'm done depolarizing, now you can do your thing. And what is missing again in this picture is, where is the delay, right? There's no delay yet. So you depolarize, you are in idle, you are listening to that depolarizing message, so you jump to conduct, you issue act node instantaneously, and this transition is taken at the same time when this message was issued. Because this automata is not consuming any time cycles yet. Okay? So let's fix that. So I present to you an updated path automata with its own clock called Z. And now let's play the entire simulation again in our minds, right? So you'll get tired of me saying this, but that's the whole point. I want you to be able to wake up at 4 in the morning and be able to do this. So we are in rest period, the SA node. This is the only condition, or this is not the only condition. The SA node can also listen to depolarize, but the rest period of the ventricles is higher, so this is the condition that will trigger this transition. When this transition is taken, we of course have to reset the clock because we are going in a new state. We issue this message called depolarize. And who is listening to this message now? It's my path automata. In fact, the only guard condition is if you hear from the SA. There's no clock here. Otherwise, you remain idle. There's no reason to propagate anything. When you do hear this depolarized message from the SA node, you go into the state or location called conduct. And the reset is that you're setting the clock. Actually, this is incorrection. This should be a definition rather than an assignment. So we assign Z to a conduction delay value, and we move into this new location called conduct. All this time, our ventricle is just counting down. It's just doing its rest thing. There's nothing interesting to do there. So let's say this is 100 milliseconds based on the property of the AV node. So once we are done conducting, we will go back to the idle state when this guard condition is satisfied. So our conduction clock has counted down from the default value. And now when we go back to the idle, we issue a message specifically for the ventricle. We say activate node 2. Now, assuming that this hasn't expired, which is why we have a larger rest period, the ventricle will make its depolarizing transition because it has received this message. And so what has effectively happened is our atriums triggered, there was a delay, and then the ventricles triggered. So I see I'm losing some of you, so time for questions again in this picture.
Is there a reason we don't just draw all these as like one integrated model? Like, as like, instead of like these 3 separate blocks, like I know we want to have them repeated, but why not just connect them all?
Okay, you just jumped like 4 lectures and we will get there. But the question was, why even bother having 3 systems in parallel? One example is it's more easy to understand, and because it represents a real physical system, so you would want to analyze the properties of the tissue separately. Also, you would want, as a mathematical object, you could do what is called a product automaton, which is given n automatons, I want to represent them as a single object. But it would be very difficult in this context to wrap your head around how things are transitioning between all of those. Right? So it's best to decouple based on the functionality of the hardware. But we will need the need for a product automaton just when we do model checking. So we will cover a little bit of that. Is everyone convinced that this stuff can replicate the timing properties of normal sinus?
Like for the Y time automata,
Yeah.
so like when you go from rest to ERP,
Yeah.
like you say like depolarize there.
Yeah.
Like is that like supposed to be there? Kind of confused.
Okay, so question is that we looked at this direction of depolarization, which is called what? Just my own sanity check that people remember. Anti-grade conduction. But there still seems to be, we sort of hacked around the fact that let's just rename something specific to node 2 and that would work for normal sinusoidal, no problem. But I have the habit of presenting stuff and then breaking it to tell you how to fix it. Let's actually look at retrograde conduction in this model. So what happens if, for some reason, from irritable tissue or for some reason, the SA node doesn't get to fire first. It's the ventricle which fires first. What happens in that situation? Right, so the ventricles clock expires sooner, and in this case, you may not be directly using this node for the right ventricle apex, but maybe for some irritable tissue, for example, in the ventricle, what have you. But this is the first thing that happens in our picture. So when that happens, we issue a depolarize, but our path is an idle. It will listen to my depolarize. It will go to conduct, and then when it comes out of conduct, it's not going to trigger anything with the SA node. Because when it comes out of conduction, it's passing a message back to the ventricle. That's not what we want. In retrograde conduction, we want the ventricles to go trigger back in atrium. So you are right. It's not, everything still doesn't, match up when you have to think of something outside of the normal sinus. So how do we fix it? Well, we do the same thing as before. I add a mirror conduction path where I want to fix the problem by saying that when you go through this conduction path and come out of the delay, you say something called act node 1. So we should change this message and this message to activate node 1. So let's do that. Oops, I'm sorry. Yeah. So what I have done now is, this is still the same. This is still the same as before. But to look at our right ventricle node, it is issuing this message called depolarize, which is going still through our anti-grade channel because we don't have any actually transition here. So let me actually skip forward until, I think this is where we fix it. All right, so what has changed, right? So we have, this is our updated picture of the path automata. This is our path automata. Let's look at whether it actually resolves retrograde conduction. So in retrograde conduction, this is the first thing that will happen because the ventricles will depolarize before the atria. When that happens, you issue a message called activate path. So who is listening to activate path 2? When you are in idle, you are listening to activate path 2, and when that message is received from the ventricles, you go into retrograde conduction. In retrograde conduction, you stay for this amount of time because of the reset. You come out of retrograde conduction and issue activate node 1 message, which was earlier called depolarize. Now when you come out, you issue activate node 1. I haven't updated this. This should be, okay, this is the correct picture. I apologize. I have these intermediate slides. Yeah, so we are finally at uniform naming for good. right? So when you issue activate node 1, the SA node is listening to that message. And so in your retrograde conduction, again, you have ventricle, you have delay, and then you have the atrium. Let's just make sure that this also still works for normal sinus rhythm. So in normal sinus rhythm, this would be the first thing that would happen. Here you would issue activate path 1. So activate path 1 is being listened to in the antigrade section of the path automaton. So you are decoupling retrograde and antigrade just by playing with the names of these messages. And so activate path 1, you will go into antigrade, you will exhaust your clock, you will come out, you will issue activate node 2, which is being listened to by the ventricle, then the ventricle will trigger. So our antigrade and retrograde conductions both work. Just by naming the messages appropriately. So, questions on this? Is this clear why this path automaton makes sense? So what can this model do? Already this model can do normal sinus rhythm, it can do retrograde or some premature ventricular complex symptom. It can do all of the symptoms yet, but it will soon. But the take-home message, and once again, I know this material is dense and it's conceptually very logical, right? We want to be very precise. There's no room for ambiguity, and all of that precision happens because of the canonical objects which define the time atom. This is the new way of modeling things. So one can question and say, well, what can you? The questions that we had earlier. Well, this rest period is not fixed. This ERP period is not fixed. So the beauty of this time automata is that when you are in a certain state or a location, you can do other things as well. Right now, we don't care about that. Right? So when you are in ERP, nothing interesting is happening. I could have a machine learning model inside my ERP location, which will determine what should be the new ERP rest period. That's possible, but let's not get too excited. Okay, so we have our Lego blocks, which are timed automatons. What we have studied today is that because of functional syncytium of the tissues of the cell, we can use this rest ERP RRP block, place it anywhere we want, but we also need another block called the path automaton, which looks at the properties of the delay, right? So this 100 milliseconds AV delay, for instance. So I will stop here, and we can pick up other stuff starting next Tuesday, where we will finish our timed automata and also release the first worksheet for this module. Just a preview on what's coming next. Everything seems great, right? 2 thumbs up, retrograde, antigrade. But here's some food for thought. You may want to think about this now or later. There's a big problem that exists in this picture. And it's not very easy or subtle to look at. The problem is that there's actually an infinite loop which can arise out of this, where you go from antigrade back to retrograde, back to antigrade, back to retrograde. And we'll discuss why that exists, how we fix it, and move on from there. Time permitting, I will also show you this model in simulating state flow in the next lecture, or maybe for sure in the next week. But this was the first introduction. This was like a different way. Earlier on we separated our discussion of what stage space is and then how we applied it to the building. Here we are kind of doing stuff in parallel, right? We are learning about the heart and modeling it at the same time using this new tool and machinery. But this is a very powerful way of modeling things in terms of their discrete sort of events or locations or states that they visit and how they cross-talk to each other using timing and messages. So let's pick this up in the next